Okay, so we're going to do a problem, and what we're going to do is consider some metal sphere of radius r, and it carries a charge q. This sphere is surrounded by a metal shell, but the shell carries no charge. And what we're going to do first of all is find the surface charge density sigma at r, at a, and at b. Okay, so what's our total charge going to be equal to? Well, our total charge q is going to be equal to the integral of sigma over the area, and that is going to be given by sigma by 4 pi r squared. Okay, where r is the radius. So let's start at, for big R, so we have r is equal to capital R. And what we're going to find is that our surface charge density sigma will equal q divided by 4 pi r squared. Now what happens at r is equal to a? So at r is equal to a is quite interesting because initially it carries no net charge. But of course, since we have a positive charge on our metal sphere, we're going to induce a negative charge on the inside of that metal shell. Okay, so whenever r is equal to a, sigma will equal minus q divided by 4 pi a squared. Okay, so again, the negative charge comes from the fact that there's been an induced charge on the inside of that metal shell, which has been caused by the positive charge at caused by the positive charge of the metal sphere. Now for the third one, whenever r is equal to b, and now since we've got a negative charge on the inside of our metal shell, we're going to have a positive charge on the outside. So sigma will equal to plus q divided by 4 pi b squared. Okay, so now that's the first part of the solution. Now for the second part, we want to find the potential at the center using infinity as our reference. Okay, now let's set this up. Okay, so our potential is going to be equal to minus the integral, and we're coming from infinity into the center of a sphere, so we go from infinity to 0 of E dot dl. So now what we're going to do is we're going to break this up into a number of different integrals, and we're going to calculate the potential at different points. So from infinity to the surface of the spherical shell, from the surface of the shell to the inside surface of the shell, and so forth. So now what we can write is our potential will be equal to the integral. Now the first one's going to go from infinity to the surface of the spherical shell, which is b. We have 1 over pi epsilon naught by q over r squared for electric field dr, minus the integral. Now we're going to go from b to a, so we go from the surface of the shell to the inner surface of the shell, and we're dealing with a conductor here. Now remember that the electric field inside a conductor is going to be equal to 0. Okay, so what we have here now is the integral of 0 dr minus the integral from a, so from the inside surface of a spherical shell to the surface of a sphere, dr, and the final integral that we have is for inside the sphere itself. So here's where we're going from r into 0. So we go minus the integral from r to 0. And of course we're dealing with a conductor here again, so our electric field inside is going to be equal to 0. Now, whenever we work out these integrals, what we're going to find is that our potential is going to work down to 1 over 4 pi epsilon naught by Q over B plus Q over R minus Q all over A. And that's our final answer.